This is Official Nerd Business.
Hello nerd boys and girls, and welcome back to another one of our Euler videos. Today we will be taking a swing at Euler problem number 36, double-based palindromes. We will be doing so using Python 3 in the PyCharm IDE editor. Well, it's been a little while since I've done one of these videos. It's been about a month, I guess. I've been between computers, as it were. Ordered a new computer, something went wrong with the order. I had put some time in to correct it. But now we're back from outer space, and we will be taking a look at problem number 36. It's a problem at first that might seem a bit simplistic. It's easy to write a loop that exhaustively tests everything that Project Euler wants us to test, and after you've put in your answer, you are given an overview, and this overview helps open completely new doors on this particular challenge. It lets you see this problem in a completely new light, so that's kind of fun, and I want to run through both of those solutions. So attempt number one will be what you might code up for yourself, and attempt number two will be slightly more involved mathematically speaking. So let's have a look at the problem. The decimal number 585 is also represented in binary, and it's palindromic in both bases. So in binary is also called base 2, so there's only two numbers available in a base 2 number, that's a 0 and a 1. And how can we construct numbers higher than that? Well, we could simply put two ones, which means that there's this basically works the same as decimal numbers, where every spot in a decimal number equals 10 to the something power. So something to the 0th power is 1, so this denotes the ones. So we have d1s plus 10 to the first power. Double start, of course. And here we have then 10 to the first power, so c denotes the number of tens that we have. And here we go for 10 to the second power. B here denotes how many hundreds we have, and I've also put up an A here. So if we were to fill in some actual numbers here, we might take a look at 5, or in fact the 585 in the example doesn't have any thousands, it has 5 hundreds, it has 8 tens, and it has 5 ones. That's how decimal numbers are built up, but we can do the same as we did here. For twos, and as you can see, I'm gonna put decimal values up here. So 2 to the 0 power still is 1, and then there's 2 to the 1, which is simply 2, then 4, and then 8. As you can see, all the powers of 2 will show up here. Obviously, so we could construct a number here by using only zeros and ones. So note that for any single spot you could not put in a 10, because that would overflow. We are counting up to but not including 10. There are 10 digits available, ranging from 0 up to 9. So here are 2 digits available, ranging from 0 up to 1. So we could put in a 1 here, for instance, and a 0 and a 0 and a 1, and we would have constructed the number 9. By the way, this is palindromic. So that's what binary numbers are. They are a collection of zeros and ones, which when their position is measured against the corresponding power of 2, you get a number back out of them in decimal notation. There's your crash course on binary numbers. And the number 585 is kind of special in that it is both the palindrome 585. Palindromes you've seen before, it's when you reverse it, you get the same. So when we reverse 585, it says 585 again. And it's also palindromic in base 2. So it yields a number 1001001001001, which if you flip it, you get exactly the same number back. So there's the problem, and the challenge is find the sum of all numbers less than 1 million which are palindromic in base 10 and base 2. And this is a special good clause to have. Please note that the palindromic numbers in either base may not include leading zeros. And this is important because this means we can't create the number. Sometimes you will see that a binary number is padded out to 8 or 16 digits. Those are called bytes in computer speak. And those would include leading zeros if the number itself was less than 255. But this is not allowed. So we can't have leading zeros, which means we can't have trailing zeros, which means that all of our palindromic binary numbers are odd numbers. There has to be a 1 at the end, and as we've just seen, excuse me, those should be stars. This is 1, so there is a 1 at the end, so whatever number you are creating with whatever cruft is before it, you will add a 1 to it, making it an odd number. So how we would go about this? We could have a simple loop construct, I guess. Let's actually give parameters to a range. We want to start at 1, want to carry on up to and include our limit. Less than 1 million, we don't want to include the limit. And we want to only look at the odd numbers. If we run this, you can see, by the way, I've used my boilerplate code for this, so we are running this, and when the file itself is called, when we run it from main.py, this little bit gets called. Using this default parameter if you don't specify anything else. But when we run this file on its own, this bit of code is triggered, which also executes this, but with the parameter specified here, and I've limited this to 100 for the time being. And as you can see, this code does nothing but print whatever value I assumes in this loop, and it's all the odd numbers. Now we're going to check if this is palindromic. If let's make this into a string, and if this string is exactly equal to itself but in reverse. These are list slicers, which also work on strings because strings are most of the time basically lists. And this should give us all the numbers below 100 which are palindromic. All odd numbers below 100 which are palindromic. And it does so 99, 77, 55 and all the single digit odd numbers. List slicers, you can specify from a list which elements you want to take. So if we were to select from a certain starting position, we could specify it before the first column up to a certain position in this collection, or in this case a collection of characters, so start string we could specify here, and step size we specify here, and if step size is negative it jumps backwards. So in this case we tell it to reverse the string by not specifying a start or an ending index, so it takes the entire thing but with a negative step, going backwards one character at a time. So if this string is equal to itself reversed, then we have a palindrome on our hands. Now we want to know if the palindromic or the binary representation of this number is also palindromic. And there's a very nifty, neat, handy function in Python to do this, which is simply called bin. and bin converts any decimal number into a binary number. To demonstrate, let's put it on the screen real quick. And here's all the decimal representations, or all the binary representations of the numbers. In fact, let's throw in the numbers themselves. Here's for 1 its decimal representation and its binary representation, and for 3 and for 5 and for 7, etc. Now note that the bin function, it does not return an actual number, it returns a string. And at this point, for a computer, the binary representation or a decimal representation are just that, representations. But the actual number is stored in a number type on your computer, and it's all zeros and ones there anyway. So a representation is only showing how a number would look given base 2 or given base 10. Base 10 is our default, and when you convert it into a binary string, you would expect a string like this, but if we were simply given this number back, we would assume that this is again decimal. So if we were to, this is 1 plus 5 is 16, 21. If we were to convert 21 from binary, or from decimal into binary, and treat this as a number, it would again be seen as a decimal representation by Python and actually assume this number in decimal. That's not what we're after. So what does Python do? Python returns a string when we call the bin object, or the bin conversion. This is now a string for all intents and purposes, and we can manipulate it as a string, which is a good thing because, as you can see, in its string representation of this binary number, Python introduces the 0b, where the b stands for binary. And we don't want that, because if we reverse this string, we will never find matches because there are no b zeros at the end. So we can chop off the OB bit, and we could do that by telling it to another list slice, start at character number 2, and then do nothing else, so run all the way up to the end and in its original order. And if we were to run this now, we would see that it prints the strings out of the binary representation without the annoying 0b at the start. And now we are on the home stretch, because if bin I is equal to, again, bin I but reversed, then we know that we have a two-way palindrome. And I should add that. So here's all the palindromes in base 10 and base 2 below 100. As you can see, this number is palindromic. This obviously is palindromic. Thins out the selection a bit. Now we need to sum them all, so let's have a value r starting out at 0, and if this is a valid bingo, then we want to add I. I is the only number in this entire loop. We've converted it a couple of times and checked if it's equal to its own reverse, but I itself is still only the only number that we are interested in, and now we want to return I. Running this for 100 gives us the answer of 99. Wait, we don't want to return I, we want to return R. There we go. Yes. And this should be it. Let's see what happens when we fire up main.py. I would very much like to run problem 36 with the default parameter. And there it is. It took us 0.16 seconds to find 872,187. And I can tell you right now that if you go over to Project Euler and you enter this as the answer to problem number 36, you will see the green check. And with the green check you can find an overview, and in the overview a different method of finding palindromes is described. What's wrong with the method we're currently using is that we are testing every number below our limit, so up to 1 million in the case of the full program. But we can be a lot more efficient than that, and that's because we can generate a palindrome. We don't have to test if I happens to be a palindrome. We can start with any I and make it into a palindrome. So how will we go about that? Well, the structure for a palindrome is simply said ABC CBA, where this can be any character. So if we were to take the number ABC, we can simply flip it and concatenate it to itself. And we can do so string wise, but we can also do so arithmetically. Excuse me, that's a hard word for a non-English speaker. And we are going to do something of the sort here. Let's first create a function, make palindrome for any given n. So how can we, if we get in the number 654, how can we turn this into 654456? Well, I'm first going to grab a copy of whatever number we get in, and then I'm going to manipulate the original number we got while n is greater than 1. Should this be 0? We're going to see in a second. Now, whenever we enter this loop, we already have the first bit of our palindrome stored in R, and we want to append a little bit to the end. So we want to get the 4 off of this number, and we can quite simply get it by let's introduce a variable called a, and this is our number modulo 10. So if we were to divide this number by 10, we would have a remainder of 4, which we get by the modulo expression, and we want to add that 4 to our current the number we are prepping to return. So we can say that R is R times 10. So we plus a. So what this does is it gets whatever it currently is in R. So at our first iteration it's this. It adds a 0 to it by multiplying it by 10, and then adds 4 to that, making the last spot into what we want here. And then we want to do this trick again on this. So we go and take our n value, and we will integer divide this by 10. So it's going to divide by 10 and result in 65.4 obviously, and integer divide drops the remainder here, the decimal part. So we are left with this, and that should do it. Return to sender, return R. And I'm just going to test this. 654, and this will not fact, this should not return that number 1 anymore, but it should return 2. Alright. Oh, hang on. While n is still anything more than 1. And now I'm wondering if that should be a 1 or a 0. What does this button do? Yeah, that's wrong. This should be 0, I guess. Yes. Alright. This does what we wanted to do. If we enter 154, we get back 154451, which is palindromic. Great. And now we want to set a loop variable to 1. And we want to make a palindrome out of it. And let's call that P for palindrome. Well, P is less than our limit. Obviously, the palindrome will quite quickly grow in size, and once that hits our limit, might be exactly, in fact, I set Q right. We can set up a loop with this instead of just having the 1 number. Or well, wait, not a loop, I guess, because the while loop already is our looping construct. We could have the Q at 1 again, and then just increment Q here. This will guarantee that we hit every Q, construct every possible palindrome out of it, and as soon as that palindrome exceeds our limit, then we quit. And we need to make another palindrome out of this, and whatever we're gonna do with this palindrome is gonna happen up here. Alright. So what is it that we're gonna do with this palindrome? We know for sure, guaranteed, that this number is palindromic in base 10, but we don't know that yet for base 2. So we are simply gonna copy this a little bit, which is taking the binary string and chopping off the B0, and then checking if reversing it still yields the same result. And we need an R variable up here for the result then. And the number that turns out to be palindromic in both ways is the number that we've made into a palindrome, not the number used for generating it. Let's see if this does what we want it to do. I'm just gonna run this through its own file. It's gonna run up to 100, and previously we had 157-ish, I believe. Now we get an error. I is not defined. Oh, here's a lingering I. We are going to make that into P instead. 132 for all the palindromes below 100, base 10 and base 2. That's incorrect, and I think I know why. We are currently turning ABC into the palindrome ABCCPA, but there obviously is another palindrome we can make from an ABC stem, and that is the 5-digit palindrome where a single C is at the center instead of a double C here. And we can implement that through our make palindrome function. So we have the 1n, and then we can make an optional parameter for is odd length. let's say that defaults to false, and if it is odd length, note that down here we are again the 654 example. We are taking the last item by modulo and then dividing it by 10 to cut off the last item. And in the ABCBA pattern we don't want this the first time round, so if it is odd we are simply going to do this, chop off the last digit without appending it to our result and without separating the last digit, or the other way around, without separating the last digit off of it and adding that to our result. So we are simply going to drop one item off of n and then carry on. And down here, basically we want to run through all of this code twice, and copying and then pasting code for doing things twice is ill-advised. So let's make let's do this instead. We are going to set up a loop. It's a for loop that's going to take every item out of this list, and this list will only hold the constants true and false, and put it into this is odd variable. Then we're going to construct palindromes. First we're going to make all the odd length even odd length is true, all the odd length palindromes, and then we're going to make all the even length palindromes. And if we run this up to 100, we will get the result. That's a bit on the high side. So I'm gonna do some debugging here. I don't get why this. It's messing something up here with the 9s, because the odd length 9 should return us not 99 but just the one digit 9. So now we're doubling our result instead of getting the single digit palindromes. I was expecting 11 here as well. This is a bit odd, really. Oh, right. There is our problem. Oh, yes. That's better. So now we have the odd length palindromes all generating the odd length palindromes, and the even length. Works as expected as well. So we can get rid of this debug statement and then check if we run this, if whether or not we will get the same result. Run main 36 please. Attempt number 2 is in our code, so that's nice. Default input. And we get the same result, and we get it in about 50 times faster than we had previously. So that's quite the improvement. The limit for this problem is defined by Euler, by the project Euler website, to be quite well runnable with our primary brute force approach. But making this even go up to 10 million or 100 million is practically undoable for the code we had at attempt number 1. So then attempt number 2, the setup for attempt number 2 really comes into play, and it's really a much stronger and more elegant solution if we take another closer look at how palindromes are constructed. And yeah, you can see how you can limit the number of test cases with this loop as opposed to this loop. So as said before, it's quite easy to brute force this, and you might think you're done with it, and Project Euler shows you another way in their overview, and I think it's the wording is not, it's pretty technical, it's pretty, you might not get it at first read, so I hope this video helps in understanding how their second approach works, even though we might have hit a little error left or right. I hope the approach here is clear, and I hope you're as intrigued as I am by learning new ways to do things that seem done at first. And the optimization here, it's quite a leap, so that's pretty impressive too. That's it for number 36. Don't forget to check out my GitHub, where you can read back all of the source code and clone the project if you'd like. Obviously try to make this for yourself, but if you get stuck somewhere, have a look at my code over on GitHub, link in the description. And I will see you again next time for problem number 37.
Thanks for watching this video on Official Nerd Business. Don't forget to like and subscribe and click the bell icon. Did we discuss everything you wanted to hear, or did we miss anything? Any topics you want to hear in O&B? Leave your thoughts in the comments. See you next time.